Hello and welcome. In this problem, we have two different rigid tanks, one containing ethane and is pressure and temperature supplied, another containing oxidizer, which is an equimolar mixture. That means for each kilomole of oxygen, there is 1 kilomole of nitrogen. We have only 10 kg of that. We are asked that, when they're joined and then as combustion occurs, we are asked to find the heat transfer and the final pressure if the final temperature is 500 Kelvin. So we'll treat both the tanks together as our system with these individual subsystems here. But the challenge here is to set up the reaction. So let's go about it. What we'll do, first we'll find out what is the theoretical reaction. Of course, the reaction is assumed to be complete in this case. So we'll first find out what is the theoretical reaction and then check if for 10 kg of oxidizer, if we have any excess oxidizer or not. In other words, we'll try to find lambda, and once we know lambda, we'll redo the reaction to get the correct reaction. Okay, so we go ahead and launch the appropriate test step. In this case, again, we'll follow the closed specific branch and combustion and chemical equilibrium covered here. Now, chemical equilibrium is an IgE model, so let's exclude that. For all kind of reaction where you know the product's composition, we have either non-premixed or premixed combustion. In this case, of course, we'll again have premixed combustion because these two tanks, fuel and oxidizer, will first mix and then they will react. So if Cp and Cv are variable, then we launch the IG model, the ideal gas model. And here is the app. So we start by ethane, and we want to set up the reaction, theoretical reaction. Okay, and let's define the oxidizer. 1 kilomole of this is the proportion basically. So this is our oxidizer, and now you have to balance complete combustion with known excess deficient user defined oxidizer. Of course, this is the theoretical, lambda equals 1 in that case. So this will be our theoretical reaction. As you can see here in the bottom, methane is reacting with equimolar oxygen and nitrogen, producing CO2, H2O, and nitrogen. There is no leftover fuel, no leftover oxygen, and hydrogen and carbon are fully oxidized. That's the definition of a complete theoretical reaction. Instead of with air, this time we have a special kind of oxidizer, which has the equal number of kilomoles of oxygen and nitrogen. So the air-fuel ratio has been found, which is 6.98, as you can see here, which means for 1 kg of ethane, we need 6.98 kg of this mixture. However, we are given 10 kg of mixture. Therefore, we can calculate lambda immediately. Lambda will be 10 kg divided by 6.98. Oops. And that you can calculate to be 1.43 or 143%. With this knowledge, let's go and redo the equation. So what we'll do, let's super initialize everything. Again, we'll start ethane. We'll add ethane, and the oxidizer, let's define 1 add, and then this time when we do complete combustion with known and excess user defined oxidizer, instead of 100%, we'll say we have 143% executed. And this time, when you look at the reaction, there'll be some oxygen left over because you have excess air here. So in this entire system, if you notice, look at the total amount of product. So there is about 333 kg of products, and there is 300 kg of oxidizer and 30 kg, about 30.1 kg of fuel. But in this given problem, we really have 1 kg of fuel and 10 kg of oxidizer, 11 kg altogether. So to set this right now the reaction is based on 333 kg of reactant going to 330 kg of oxidizer. So to balance the reaction correctly, to reflect the amount of mass we have, we'll multiply the entire reaction by a factor which should be 11 kg divided by 330.1. That'll be close enough. So now by multiplying by this small factor, what we got is we'll have exactly 1 kg if you calculate of ethane here, and we'll have exactly 10 kg, approximately almost 10 kg of the oxygen nitrogen mixture. Of course, you could manually figure out this reaction and just enter this many kilomoles of each components for the reactants, these components for the this for the if you manually do that, let me just repeat, for the fuel you enter this amount, so many kilomole. For the oxidizer you pick oxygen and nitrogen and enter these two amounts, and for the product you select H2O, enter this, enter that. For CO2 enter nitrogen and enter O2 of this amount. This tick mark, by the way, means the reaction is balanced. The program does check for that. Okay, so let's now go with the hard part over. Now all we need to set up is the initial and final state. For the initial state, what we got, first we have to calculate the states. Is given 100 kPa and 300 Kelvin is our reactants. So we have found the volume of the tank. This will be the total volume, obviously, of both the tanks. For the second state, for the product state, we know that the volume is going to be same because these are rigid tanks. Volume one means here the two volumes together, obviously. And we don't know the final, we know the final temperature to be 500 Kelvin in this case. So the final pressure is found. And to find the heat transfer, we go to the process panel, load state 1 and state 2 as our beginning and final states. And that basically does it, because now we know there's no boundary work. I mean, the calculator can figure it out, the app can figure it out, but you could also enter 0 because volume remains constant. So therefore we found the heat transfer to be quite high. You can see it's about 45.75 million joules. So therefore we have found the final pressure in the state panel. As you can see, it's 174 kPa, and the heat transfer in here. If it were a problem of finding the adiabatic flame temperature, we would have entered Q to be 0 and solved the energy equation here, which would have produced E final or E3 in state 3, and that's how the problem would have been closed, finding P3 and T3 in that manner.